Okay, so we have talked a bit about the qualitative electrostatic force. So opposites attract each other and like charges repel each other. But that is not very quantitative. We would like to be able to find the strength or the magnitude of the force in addition to the direction. So if we want to find the magnitude of the force between 2-point charges, we use Coulomb's law. A point charge means that all of the charge is located at a single point in space, which is an approximation, but if we have a small object, especially a sphere, this turns out to be a very good approximation, and it allows you to find the strength of the force. So, Coulomb's law says that the electrostatic force between two charged particles is equal to the Coulomb's constant, which is 9 times 10 to the 9th Newton meters squared per Coulomb squared. So to find the force, you multiply the Coulomb constant, K sub E, times the absolute value of charge 1, which we label as lowercase q sub 1, and the absolute value of charge 2, which we label q sub 2. The charge is measured in coulombs, and then we divide this by the distance between the 2-point charges and square that distance. And so this gives us the force with the units of newtons. So what happens when we have a positive or negative charge? Well, when we want to find the magnitude of the force, we use the absolute value of the charge. The absolute value symbol, this pair of vertical lines, tells you that just take, say, 3 coulombs. Whether it is 3 coulombs or whether it is negative 3 coulombs, it doesn't really matter. Either way, you just use 3 coulombs. So it doesn't matter for the magnitude whether the charge is positive or negative. If we want to know the direction of the force, we have to think through the charges. One of the things that can cross you up a bit is that the signs of a number can mean different things. So for example, in 201, we talked about moving to the right as a positive velocity and moving to the left as a negative velocity. We also considered moving up as positive and moving down as negative. Notice that this sign does not really tell you about magnitude, it's telling you about direction. So 5 meters per second to the right isn't really greater than 5 meters per second to the left. We just choose the right to be positive polarity and the left to be a negative polarity. So also when we talk about charges, we are talking about this sort of polarity. So I don't know, red or blue in politics, or yin and yang, something like that. We just kind of pick one to be positive and negative. If we have a negative charge, it will be attracted to a positive charge. That means we will use Coulomb's law to find the magnitude of the force, and then we will use our opposites attract law, like charges repel, to figure out which direction the force is pointing. Remember, a force is a vector, so it has both a magnitude and a direction. So to know what is really going on, we need to know both the magnitude and the direction. So in our first example below, we have a negative charge to the left and a positive charge to the right. Let's say we have used Coulomb's law to calculate the force and found it to be 20 newtons. So then, what is the direction of the force? So for the negative point charge on the left, it will be attracted to the positive charge on the right. So the force will point to the right. Then remember our notation for this. This is F12, and so this corresponds to the force on particle 1 by particle 2. So that force is going to point to the right. For the positive charge, charge 2, on the right, the positive charge will be attracted to the negative charge on the left. So this force 2-1, this force on particle 2 by particle 1, will point to the left. The magnitude of these forces will be the same, so it'll be 20 newtons for the charge on the left and negative 20 newtons for the charge on the right. If there was a third charge, then we could also calculate the force using the signs to figure out the direction of the force. And then we could add the two vectors together to see what the total force on our objects are. Okay, so now we want to look at the next set of charges. We have two positive charges. Here we know that like charges repel each other, so the force on 1 by 2 will be a repulsion. So particle 1 will be pushed away from particle 2, so it will point to the left. So the sign on the force will be negative. The force on 2 by 1 will be positive because particle 2 is repelled by particle 1, so it will be pushed to the right, and the right is positive. So yeah, this can be a little tricky. The point is that the positive and negative charges is a polarity. just like we talked about right being positive and left being negative. So to connect the charges to the direction, you have to think through the attraction or the repulsion. So the force on a negative charge can either be positive or negative. It totally depends on what the charges are around it. So in that case, you want to separate the problem. You use Coulomb's law to figure out the magnitude of the force, and then you think through the opposites attract, like charges repel, to figure out the direction of the vector. Alright, so in the questions, we will use some funny units. Our unit of force for this is going to be kq squared over r squared, and the purpose of this is to simplify the math. So if we ask for the Coulomb force between two charged points, where Q1 is 2q and Q2 is 2q, and the distance between them is 2r. So to do this problem, our unit of force is kq squared over r squared, so we use Coulomb's law. The force is equal to the Coulomb's constant, so k, times the absolute value of Q1 times the absolute value of Q2 divided by the distance r squared. This gives us k times 2q times 2q divided by 2r squared. And that gets us to k times 4q squared over 4r squared. So we simplify this and we get 1, I already got there, we get 1 times k q squared over r squared. Alright, so if we wanted to find the direction, both particles are positively charged, so they will repel each other. The main thing here is to think about these units. So what we're doing is we're setting the charge in a specific unit of q and the distance in a specific unit of r so that the math is simplified, and we can just kind of plug in these numbers and you can sort of get an intuitive idea on how these forces are changing. Notice that this is a perfectly valid unit. So you'll do some similar practice problems to introduce these units using work. And in fact, this is a common trick in physics that you want to set up units that are convenient with the magnitude that you're working with. All right, we've got a couple questions for you to do here. Good luck.